Unit 1A, Lesson 1. This lesson will align with 5.4 in your textbooks. There are two main standards we are going to discuss in this lesson. The first one, know there is a complex number I such that I squared equals -1, and every complex number has the form a plus bi, with a and b being real numbers. The second standard, use the relation I squared equals -1 and the commutative, associative, and distributive properties to add, subtract, and multiply complex numbers. There are a few terms you need to be familiar with in order to understand this lesson. The first one is a complex number. Complex numbers account for every single number we work with, whether they are real or imaginary. That brings us to our next term, imaginary numbers. This is going to involve that letter I that stands for an imaginary number, the square root of -1. Complex conjugates, we'll discuss that later in this lesson. The associative property, that's something you should remember from Algebra 1 and even back to middle school. If we're adding three numbers together, it doesn't matter if I add the first two numbers together first or the last two numbers together first. Since we're adding, we're still going to have the same sum in the end. That applies to multiplication as well. The commutative property, referring to addition and multiplication, doesn't matter if I have a plus b or if I take b plus a, we're still going to get the same answer in the end. And then the distributive property, if I have a number 2 times, in parentheses, 3 plus 4, we need to make sure we distribute that 2 to the 3 and to the 4. That's our distributive property. So make sure you understand all these terms by the end of the lesson. If you don't, make sure you write down questions referring to them. In these first examples, we want to use the imaginary number I to rewrite the expression as a complex number, and we want to simplify all radicals. Recall that I is equal to the square root of -1. We talked about previously, we cannot take the square root of a negative number. This is where we're accounting for that. It's imaginary if we have that. First number we're going to work with, the square root of -4. We want to break this radical up. -4 we can break up into 4 and -1. So I'm going to write the square root of 4 times the square root of -1. The reason I'm going to do that is we know what the square root of 4 is. That is equal to 2. And we just discussed the square root of -1 is equal to I. So the square root of -4 simplifies down to 2i. Next, we want to simplify the square root of -11. We can break this up into the square root of 11 and the square root of -1. The square root of 11 does not simplify any further, so we just leave that as the square root of 11. The square root of -1 we said is I, and that is our simplified complex number. Normally, you're going to see this written in a different form. You will probably see this written as I times the square root of 11. The reason we're going to put the I in front of this is if you don't close off this square root symbol and you get sloppy, this may look like the I is underneath the radical, which it is not. So that is why we're going to, in standard form, write the I in front of the radical. One more example of this, we have the square root of -8, which we can rewrite as the square root of 8 times the square root of -1. We can simplify the square root of 8 because it has a factor that is a perfect square. So we write this as the square root of 4 times the square root of 2. We know the square root of -1 is I. We know the square root of 4 is 2, so we have 2 radical 2 times I. We just discussed we want to write this I in front of the radical so there's no confusion. So we have 2I times radical 2. So we took the square root of -8, broke it down, simplifies down to 2I times radical 2. In this next example, we want to add or subtract the complex numbers, write your answer in the form a plus bi. We call a plus bi, a stands for the real part, bi stands for the imaginary part, a and b represent real numbers. So if we're in the form a plus bi, we have 2 plus 3i plus quantity 5 plus 4i. What we're going to do when we add or subtract complex numbers, we have 2, which is a real number, and 5, which is the real part. And then we have 3i, which is imaginary, and 4i, which is imaginary. We're going to add those corresponding parts together. So to add these two complex numbers, we're taking 2 plus 5 to get 7, 3i plus 4i to get 7i. Next, we want to take the quantity 6 plus 4i and add 8i to it. Just on a side note, if we look at 8i, that's not written in the form a plus bi, but this would be the same as 0 plus 8i. Okay, so this is still in the form a plus bi, it's just that the value of a is 0, so it's pointless to write that in there. So when you see that, you need to recognize this is still in the form a plus bi. Now getting back to this problem, we still add corresponding parts. 6 is the only real part, so we have 6 plus 4i plus 8i. 4 plus 8 is 12i. And we are in the form a plus bi. Value of a is 6. The value of b is 12. In the last example, we're going to do a subtraction problem. We have 2 plus 9i minus the quantity 3 minus 4i. If you remember from algebra, if we're subtracting a quantity in parentheses, we can change this to an addition problem. We do that by changing this to addition and changing the sign on every value inside the parentheses. So this would become a -3 and this would become plus 4i. We're taking 2 plus a -3i, which is going to be -1. 9i plus 4i is going to be 13i. The value of a is -1. The value of b is 13. That's how to add or subtract complex numbers. Next, we're going to multiply complex numbers. We want to write the final answer in the form a plus bi. In this first one, we have 3 times 4i. All we have to do is multiply the coefficients. So 3 times 4i is going to leave us with 12i. In the next part, we have 5 times the quantity 3 plus 7i. This is where we're going to use the distributive property. We have to multiply the 5 to the 3, and we have to multiply the 5 to the 7i. 5 times 3 is 15. 5 times 7i is 35i. Applying that distributive property. The last example, we have 2 plus 3i times the quantity 5 plus 4i. We will need to use the FOIL method in order to multiply this out. First, outer, inner, last. Remember, F stands for first. We're taking the first terms in each of our quantities. 2 times 5 gives us 10. The O, we're multiplying the 2 outside terms. 2 times 4i is 8i. I is the inside terms. 3i times 5 is 15i. And then L stands for last. 3i times 4i is 12i squared. We can do some simplifying, combining like terms. This is going to be equal to 10 plus 8i and 15i are like terms. We can combine the coefficients. 8 plus 15, 23i. I squared is equal to -1. Because if we recall what I is, we said I is equal to the square root of -1. And then we're squaring that quantity. Well, the square root and the squared basically cancel each other out. We're left with -1. So here we have 12 times -1, which is going to be a -12. One more step. because now we have like terms again. 10 plus negative 12, or 10 minus 12, is negative 2 plus 23i. Recall the a plus bi form. Our a value is negative 2, the b value is 23. That is how to multiply complex numbers. The last part of this lesson is going to be working with powers of I. So if we have I raised to some exponent power, what we're going to do is divide the exponent by 4 to find the remainder, because powers of I follow some pattern. They're always going to simplify down to either 1, I, negative 1, or negative I. If we take the power of I and divide it by 4 and look at the remainder, if our remainder is 0, then the value of that power of I is going to be equal to 1. If the remainder is 1, it's going to be equal to I. If the remainder is 2, it's going to be equal to negative 1. And if the remainder is 3, that expression is going to be equal to negative I. So you need to remember these. These are problems that you will see on state tests, the ACT, test at the academic festival. Understanding powers of I is something that will show up later on. So you need to make sure you understand all these. We'll go through a few examples next. Last example is compute each of the following. So we're going to use those ideas of the remainders in order to simplify each of these expressions to find what the value is equal to. We're looking at the exponent value in this first one. We have I to the 7th, so we have a power of 7. What we're doing is taking 7 and dividing it by 4. This is a simple one. 4 goes into 7 one time, left with a remainder of 3. If you have a remainder of 3, should have written this down in your notes, that expression is going to be equal to negative I. So I to the 7th simplifies down to negative I. Next, if we look at I to the 9th, again, we're taking 9, dividing it by 4. 4 goes into 9 two times. 2 times 4 is 8, left with 1. If you have a remainder of 1, this expression simplifies down to just I. Now in the last one, we have I to the 49th. So taking 49, dividing that by 4. 4 goes into 4 one time. Bring that down, 0. Now 4 goes into 9 twice. 2 times 4 is 8. Left with a remainder of 1 again. So I to the 49th is equal to I as well. Notice I to the 9th, I to the 49th, because of the pattern for powers of I, they both simplify down to just I. Make sure you understand how to divide these powers by 4 to find the remainder and follow the pattern to see what they simplify down to. In the beginning, we discussed there are 6 terms in this lesson you need to be familiar with. We referenced all of these except complex conjugates. What a complex conjugate is, if we have a plus bi, our base standard form for a complex number, the complex conjugate is a minus bi. For a specific example, if we had 7 plus 2i, that complex number, the complex conjugate is going to be 7 minus 2i. The only thing that changes is the sign between our real and imaginary part for a complex number. Just want you to have a basic idea of that. We're going to use that more in the upcoming lessons. Just a recap of the standards for this lesson, you need to understand that we have a number I squared, which is equal to negative 1, because I is equal to the square root of negative 1. Our standard form for a complex number is a plus bi, with a and b being the real part, or real numbers. A is the real part, bi is the imaginary part. We also discussed these different properties we can use to add, subtract, and multiply complex numbers. And then additionally, we discussed the powers of I and use that pattern to simplify them.